Hello everybody, we're going to talk about differential equations and specifically models that involve growth and decay. To begin the discussion though, we want to talk about what we call using a method of separation of variables to solve some fairly simple differential equations. And to show you what I mean, let's start with a really simple one like this one right over here on the left. We're told that dy dx is equal to 5 minus 8x. So this is the derivative. Well, we know what to do essentially, right? That means that what we're going to do is we're going to say that in this method, dy is going to equal 5 minus 8x times dx when we rewrite this in our differential notation. And the method involves taking the integral of both sides of the equation equally. So I'm going to take the derivative of y, dy, take its integral, and set that equal to the integral of the quantity 5 minus 8x dx. Now on the left, what happens when we take the integral of dy is that we get y. Well, you could say y plus a constant, but all the constants are going to be gathered together anyways. So we'll add on any constants that we get to what we find on this other side. And of course, the integral of 5 minus 8x is going to be 5x minus 8 times 1 half x squared, which is our integral, our antiderivative of x, plus some constant. And so we're going to say that the solution to this differential equation is going to be 5x minus 4x squared plus a constant. So we get a family of curves, and this is really nothing more than a restatement of our anti-differentiation methods from earlier on when we first started talking about antiderivatives and indefinite integrals. It gets a little bit more complicated, however, when we have expressions in which y and x are mixed up together. Well, this is actually a relatively simple one as well, but let me show you what we want to do. When we say separation of variables, our goal here is to get dy, all the y terms and dy terms together, and all the x and dx terms together. So we'll start by rewriting y prime. Y prime does stand for, or is our short prime notation for dy dx, equals x times 1 plus y. Now our goal here is to gather like terms to one side. So of course I could multiply both sides by dx like I did in the last case. So I'm going to get x times 1 plus y times dx. But that's no good yet because we still see that we have this guy hanging out over here, 1 plus y. Well, we don't want expressions that involve y mixed together with the x. So what we're going to do is we're going to divide onto both sides. We're going to get an expression that looks more like this, dy over 1 plus y is going to equal x times dx. Well, in fact, this is something that we do know how to integrate, because if we now integrate on both sides, we now take the antiderivative of the expressions that we see on both sides of this equation, let's see what's going to happen. On the right-hand side, we know that we're going to get 1 half x squared plus a constant. We'll put the constant on the x side because it's a little bit easier. But what about dy over 1 plus y? Well, we've seen this before. What we would deal with is a method of substitution. And if we said that u was equal to the quantity 1 plus y, well, that's not too bad, because that means that du is equal to dy. And so, in fact, we've got the expression that looks like du over u. And we know where that leads. That is the natural log of the absolute value of u. So, just like that happened there, what we're going to get on our left-hand side is going to look like the natural log of the quantity 1 plus y. Okay, so what does that mean to us? Well, one thing that we could do now is if we wanted to actually solve for a function y that would give us this expression, we could do so as follows. Natural log of one quantity equals another quantity means that that quantity, 1 plus y, is going to be equal to e raised to the quantity 1/2 x squared plus a constant. Right? And a little further, looking into it a little bit further, that means that we're going to get something like this. 1 plus y, because it's inside that absolute value, will equal positive or negative of uh, e to the x squared over 2, I'm just going to rewrite it that way, times e to the constant c, which is interesting, right? Because remember, we're using that addition rule for multiplication, right? Which told us that if we had a to the m times a to the n, it was the same thing as a to the m plus n. We're just going backwards with that, right? That's why we can write it this way. And we're going to get y will equal to our negative 1 plus or minus, and this e to the c, well, in itself is a constant, so let's go ahead and call it just big C. Big C times e to the x squared over 2. Now, typically, we're going to just choose one or the other. We might just say, well, negative 1 plus c e to the x squared over 2 would be a solution, but that is one way of isolating c in this equation. In any case, our key step in finding the solution is to do just exactly this. Separate our variables so that y variables and x variables are on separate sides of the equation, and then go ahead and take the antiderivative on both sides. All right, good luck.